There's a strange question that's been floating around theoretical physics for a while, and that's if we could be living inside a black hole. It sounds like science fiction, but some physicists, cosmologists, and mathematicians have explored this seriously. And when we look at how galaxies spin, how the universe is structured, and how space-time might behave under extreme conditions, that question gets even stranger and more interesting. In this video, I'm going to try and explore what led to this idea and what evidence exists for universal spin and why this might not be as absurd as it first sounds. First, let me talk about galactic rotation. Spiral galaxies, like our own Milky Way, have a distinct spin. The arms twist in a certain direction, usually classified as clockwise or counterclockwise, depending on our viewing angle. If the universe were completely isotropic, meaning the same in all directions, we'd expect a random distribution of these spins, equal numbers spinning left and right. But that's not exactly what we see. In 2008, an astrophysicist named Michael Longo and his team at the University of Michigan analyzed data from the Sloan Digital Sky Survey. They looked at over 15,000 spiral galaxies, and what they found was a statistically significant imbalance. More galaxies seemed to spin in one direction than the other. This anomaly suggested something bigger. If spiral galaxies all formed from local conditions, there shouldn't be a preferred spin direction. But if this asymmetry is real, it could indicate that the universe itself has angular momentum, and in other words, it could be rotating. If the universe is rotating, that breaks the idea of perfect symmetry that underlies the standard cosmological model. Rotation would introduce a preferred axis, a cosmic spin direction. This violates the cosmological principle, which says the universe looks the same no matter where you are or which direction you look. But here's the twist. A rotating universe is entirely consistent with Einstein's equations. It was predicted by Kurt Gödel in 1949. He found a solution to Einstein's field equations that described a rotating universe. It allowed for closed time-like curves, essentially paths through spacetime that loop back on themselves, raising the possibility of time travel. Gödel's universe isn't ours. It requires strange conditions we haven't observed. But the point remains. General relativity allows a rotating universe. Now let's talk about black holes, specifically the rotating kind, described by the Kerr metric. Unlike non-rotating source-child black holes, Kerr black holes have a structure. They spin. They have an inner and outer event horizon, and inside, there's something called the ergosphere, a region where spacetime itself is dragged around by the rotation. And in some interpretations, a rotating black hole could create a spacetime region with characteristics similar to a universe. There's a hypothesis that suggests the singularity of a black hole might bounce or tunnel into a new expanding universe on the other side. That's a speculative idea, but it fits with some approaches to quantum gravity and bounce cosmologies. If you reverse that idea, what if our universe is inside of such a region? What if we're in a giant rotating space-time bubble, bounded by a kind of horizon we can't see? Michael Longo's work isn't the only analysis of galactic spin. Other studies using data sets from Pan stars and the Galaxy Zoo project also show hints of asymmetry, though the results aren't always consistent. Some papers find a mild preference, others find no strong bias, but importantly, no study has shown a perfectly balanced distribution, which you'd expect in a completely isotropic universe. The idea isn't that every galaxy spins the same way, clearly they don't, but that over vast scales there's a statistical skew. That skew could be noise, it could be data bias, or it could be a hint. A 2021 paper by Lior Shamir reanalyzed over 200,000 galaxies and found consistent asymmetry over different sky regions, again suggesting large-scale handedness. This isn't proof of a rotating universe, but it keeps the question open. Several physicists have explored the idea of a universe inside a black hole. Nikodem Poplawski, a physicist at the University of New Haven, is one of the most prominent. He proposed that every black hole could potentially spawn a new universe inside it via a process involving torsion and spin in Einstein-Cartan theory, a modified version of general relativity. In his model, our universe's Big Bang wasn't the start of everything. It was the bounce from a collapsing star in a higher dimensional parent universe. The black hole's singularity becomes the seed of expansion on the other side of the horizon. If this is true, our universe's mass, structure, and even its spin might reflect the conditions of that original black hole. In a way, the parent universe encoded its properties into us. So what would it mean if we are inside a black hole? Would we notice? Probably not directly. Inside a black hole, observers experience what seems like a normal region of space-time until they hit certain limits. But if the interior behaves like our universe, expanding, structured, obeying general relativity, then everything we see could be consistent with that idea. We may never observe an outer universe directly. Our cosmic horizon, the farthest light we can detect, is limited. We can't see beyond the cosmic microwave background, so we might be bounded by a structure we can never escape, just like the event horizon of a black hole. What about the rotation? If the entire universe is spinning, we might detect that through subtle anisotropies, like galaxy spin directions, cosmic background variations, and even the polarization of light across cosmic distances. So we don't know if the universe is spinning, we don't know if we're inside a black hole, but the data we do have and the way that galaxies rotate, the structure of space, the predictions of our best physics leave the door completely open. If it's not proof, it's not a theory we can confirm yet, but it's a reminder of how little we really know about what we're inside of, and how deep the rabbit hole of modern cosmology can go. If you found this interesting at all, I'm going to keep exploring questions like this, so make sure to stick around.